welcome everyone. Welcome back if you joined us this morning. We're still on day one. This is our second session of the day. This is from 10:30 to noon Pacific Standard Time. Today's workshop is, this session is Tire-Derived Aggregate, TDA for Lightweight Solution Sustainable Engineering. Again, my name is Tommy Amundsen. I'm the Sacramento State producer. And with that said, I'm going to go ahead and hand it back over to our MC for the workshop series, Kyle Pogue from CalRecycle.
Thanks, Tommy. Welcome back, everybody. I'm Kyle Pogue with CalRecycle, and just observing that our first session was really well done. We had over 100 participants. Do want to also recognize we weren't able to get to all the questions and answer those. We will be doing a follow-up if we did not get to your question. I want to thank our moderator, Lido, and all the presenters for all the content they provided in the last session. And now we're going to shift gears to our second session titled Tire-Derived Aggregate, Lightweight Solutions for Sustainable Engineering. And it is my pleasure to introduce Matt Weiss, the moderator for this session. Matt, thank you. Take it away.
Thanks, Kyle. Good morning, everyone. Welcome back to the 2026 California Tire Virtual Workshop Series, the second Tire Workshops session. Today is Tire-Derived Aggregate, or TDA, Lightweight Solutions for Sustainable Engineering. My name is Matt Weiss, and I'm a waste management engineer at CalRecycle in the Tire Engineering and Environmental Research Unit. Our unit is tasked with developing and expanding markets for waste tires, and TDA is one of the markets we are currently focused on. Today's session explores how TDA advances sustainable geotechnical engineering and pavement design. First, we'll hear about experimental results on TDA as a low-cost seismic isolation layer beneath shallow foundations and slabs, detailing material behavior and a forward path toward hybrid systems pairing TDA with cementitious lightweight fills. Next, we'll learn about a proposed project that aims to address Caltrans Lean Concrete Base performance, proposing fiber-like TDA particles to enhance flexibility, ductility, and energy absorption to mitigate curling and warping and slab cracking under California's temperature swings. Lastly, we'll hear from real TDA users on California case studies in Yuba County, supported by CalRecycle's TDA grant program, which shows TDA's effectiveness as a lightweight, free-draining fill material for slope stabilization. The audience will gain design insights, quality assurance and quality control considerations, and implementation pathways for resilient, cost-effective infrastructure. Q&A with the speakers today will be held at the end of the workshop after all the presenters have concluded, if time allows. Now we'll move on to our speakers for today. We'll start with Camille Gaz, assistant researcher and incoming PhD student at UC San Diego in the McCartney Research Group. Camille will present on TDA being used in static and seismic geotechnical applications. The next presenter will be Dr. Somayeh Nassiri, associate professor, principal investigator, and incoming director of the University of California Pavement Research Center. Dr. Nassiri will be presenting on an upcoming research study on the use of TDA in lean concrete base. And lastly, we'll hear from James Gomez, QA/QC manager, and Martin McElroy, geotechnical and engineering geology professional. James and Martin are both licensed professional engineers at MGE Engineering, and both were heavily involved in TDA projects that were constructed in Yuba County in 2017 to repair severe storm damage. Now, without any further delay, I will hand it over to Camille Gaz to start her presentation. Camille, please go ahead and begin when you're ready.
Thank you very much for the introduction. Again, my name is Camille Gaz, and I am an incoming PhD student at the University of California, San Diego. My PI, Dr. McCartney, unfortunately was unable to present today, so I am presenting both on his and my behalf. And I will be talking about tire-derived aggregate as a lightweight fill in static and seismic geotechnical applications. And next up slide, please. First, I would like to acknowledge the various graduate students and laboratory staff at UC San Diego who have contributed to the previous TDA research and projects conducted. I'd specifically like to name Dr. Bebahani, Dr. Goud, and Dr. Yaralman for their incredible contributions, as well as thank and acknowledge CalRecycle for their wonderful funding and support. And next slide, please. As an overview of today's presentation, I will start with looking and describing the TDA applications and advantages as a lightweight fill, and then moving into looking at the measurement of TDA properties relating to past material testing we have conducted at UC San Diego. This will include looking at monotonic and cyclic shearing properties, one-dimensional compression, and the bearing capacity of shallow footings. Then we will transition into looking at the use of TDA for geotechnical seismic isolation, also known as GSI, and end with looking at the new National Science Foundation project we have been working on at the University of California, San Diego. And this project focuses on creating a geocomposite between a lightweight cellular concrete material known as LCC and TDA for GSI purposes. Thank you. And this will include overviewing the interparticle testing we have been conducting for this NSF project, along with describing the TDA and LCC composite structure shake table testing plan. Next slide, please. Just as a reminder of why TDA is so important in civil engineering applications, the most economical reuse of waste tires in civil engineering is in specifically the form of TDA with large particle sizes. TDA has a very unique combination of favorable engineering properties. This includes it being lightweight, its favorable shear strength, it has very good hydraulic conductivity, and it has an extremely high damping ratio. I will be focusing specifically on discussing the damping ratio and what that means later. TDA, it is also to note, may deform more than soils upon external loading, and the displacement at peak shear strength is greater than in dense backfill soils. Additionally, deformation in backfill options can be accommodated through overbuild analysis or adding lightweight cellular concrete, and deformability may be an asset when using TDA as a compressible layer specifically. Next slide, please. A list of TDA uses relating to civil engineering applications. TDA has a varying amount of uses, which is why it is such a favorable material. It can be used as a lightweight backfill material in embankments or internally stabilized slopes or retaining walls, as a fill for gravity type retaining walls to reduce static or seismic lateral earth pressure. It is favorable for landslide repair and slope stabilization. It can be used as a bridging material for buried utilities. It is very good in vibration mitigation, which relates to its high damping ratio. Also, it can be used as thermal insulation or as drainage layers in landfills for stormwater infiltration, and then as a compressible layer. So it is very, very advantageous as a material due to this variability in use. Next slide, please. Next, we will discuss the geometric constraints on TDA geostructures themselves. There are two main types of geostructures that we have been studying at the University of California, San Diego. Type A TDA has a 75 to 100 millimeter particle size with a fill height limit of 1 meter, where type B is 150 to 300 millimeter particle size with a fill height of 3 meters. It is important to note that TDA layers must be encapsulated by a geotextile and surrounded by at least 1 foot of soil. However, multiple TDA lifts may be used if they are separated by soil layers. And as a takeaway, it is always recommended to use type B TDA for the best economic and performance. Next slide, please. Looking at the geotechnical seismic isolation within TDA, adding a layer of TDA beneath a shallow foundation essentially will create a compliant foundation. And this is defined as a new category of geotechnical seismic isolation technique, as it does not change the structural configuration of the footing, foundation, or substructure, as it only modifies the foundation soils itself. The use of a low modulus material such as TDA surrounding the foundation of the structure effectively decouples the structure from ground shaking via shearing and rocking mechanisms. These rocking mechanisms we will discuss shortly, but it is important to first note that as a result of this decoupling, the dissipation of seismic energy occurs before it is able to transmit into the structure, instead of using other geotechnical seismic isolation techniques, which essentially dissipate the seismic energy within the structure itself. Next slide, please. So looking at this geotechnical seismic isolation, specifically its rocking mechanism, rocking shallow footings supporting bridge columns have been proposed so that a plastic hinge develops below the footing instead of in the column. And this essentially dissipates energy during earthquakes when bearing capacity is mobilized and reduces costly damage to superstructure components. Additionally, there will be recentering as during shaking, which will minimize post-earthquake repairs. Rocking footings on soil have been widely studied within various labs, including those at UC San Diego, but issues regarding structural compatibility, settlement, and a need to control kinematic response of rocking footings still needs to be better understood. Next slide, please. Next, we will discuss the various TDA properties and conclusions determined from material testing conducted at the University of California, San Diego in the last span of years. Specifically looking at direct shear testing of a large mass of TDA particles. Here are some helpful schematics relating to the testing setup, along with horizontal displacement to shear stress relationship curves and horizontal displacement to volumetric strain curves resulting from the experiments conducted. Next slide, please. Looking at type B TDA internal and interface failure envelopes. A nonlinear failure envelope does occur from type B TDA, and nonlinear failure envelope parameters have been used to predict bearing capacity and perform stability analysis. TDA, it is also important to note TDA has similar shear strength to soil backfills, but is far more flexible. And nonlinear failure envelope parameters have been used to predict, I already said that, excuse me. Next slide, please. Looking at simple shear testing of TDA with large particle sizes, again, this is TDA type B. Main testing conclusions are that TDA has a low modulus compared to soils, but a significantly higher damping ratio as mentioned. And here are some more helpful figures from Dr. McCartney's simple shear testing of the large mass of TDA particles, including shear strain versus shear stress, vertical stress versus shear modulus, cyclic shear strain amplitude versus damping ratio, and cyclic shear strain amplitude versus shear modulus. Next slide, please. Looking at a new compression curve for type B TDA with creep from shallow footing bearing tests, it is important to note that TDA settles more than soil backfills, but an overbuild approach can be used to reach target final height under load. And then just some more important figures that relate to this testing. Next slide, please. Next, we'll break down the procedure for shallow footing bearing tests. Before seismic testing of footings in TDA, it is critical to understand the bearing capacity of footings in TDA. Tests were performed in a concrete box that was 10 feet in height by about 18 feet in length, and a 10-foot layer of compacted TDA was placed within the box. Loading was applied to the footing from a hydraulic actuator connected to a brace frame connected to a lab strong wall. Next slide, please. Here are some helpful schematics related to the bearing capacity tests conducted. The first main conclusion from these tests was TDA compresses significantly under footing load without reaching a clear bearing capacity. The second conclusion was that tilting in the footing will occur at large settlements. And then some more helpful figures on the testing procedure. Next slide, please. The measured bearing capacity when tilting failure occurs matches well with equation predictions. However, large settlements will occur at tilting failure. As a result, a new equation shown here is proposed for settlement failure criterion, and this equation relates to the Brinch-Hansen equation. Next slide, please. Seismic testing of footings in TDA were conducted at UC San Diego's South Powell Laboratory shake table. 3 TDA layer thicknesses with different A versus AC ratios were conducted, and results showed that smaller A versus AC ratios implied lower static factor of safety with more rocking expected during earthquakes. And then just some more helpful photos of the experiment. Next slide, please. Here are some more photos of the experiment. Okay, next slide, please. The final conclusion on the rocking response of footings is that smaller settlements with greater reactions occur in footings on TDA as compared to footings on soil, and that TDA has an excellent recentering capability. And this is supported by the 2 graphs looking at the A versus AC ratio relating to the recentering ratio, and the other figure, which looks at different sands versus clays versus type B parameters, or type B TDA parameters. Next slide, please. Now I will introduce the new NSF project we are currently researching at UC San Diego. Again, this project is generously funded by the National Science Foundation. This project aims to develop a geocomposite or composite fill between TDA and LCC, or lightweight cellular concrete. The aim of this geocomposite is to maximize the advantageous effects of each individual material while minimizing the less desirable material effects. This composite is intended to gain the vertical stiffness of LCC under normal loading, combined with the horizontal flexibility of TDA under shearing. The aim of this geocomposite is that its installation under foundations would effectively apply the geotechnical seismic isolation properties of TDA in order to effectively dampen seismic activity before reaching the foundation or substructure. And these figures exemplify potential sectional layouts of the TDA and LCC composite. This includes a mixture approach, a geometric layered approach, a more traditional layered approach, and please note the use of geogrids and geomembranes is crucial within this composite. Next slide, please. As a project overview, LCC, for those who do not know, is a lightweight cementitious material consisting of Portland cement, water, and a foaming agent, which results in a high compressive strength, but a unit weight similar to that of TDA. This NSF project will be utilizing discrete element modeling, or DEM simulations, used to study different composite architectures like the ones mentioned earlier. Interparticle testing will be conducted to get new contact relationships between the LCC and TDA particles, and models of TDA and LCC together will be used under static and cyclic loading within PFC. Then a shake table testing combined with compressive loading to understand the composite behavior will occur. Next slide, please. The interparticle testing of TDA type B particles include testing different TDA shred types at different orientations, including face, back, and edge. These tests include normal compression of both individual and pair particles, shear testing, and three-point bending tests of the particles. Next slide. Key findings from the normal compression tests were the hysteresis observed regardless of the normal stress range applied to the particle pairs, and that different particle pairs and their orientation had major effects on the normal stress strain curve. Next slide, please. Key findings from normal compression tests were that a model combining a hyperelastic stress strain curve with a Maxwell viscoelastic model was found to provide a good match to the experimental data as well. Next slide, please. Then key findings from the shear tests were that a nonlinear failure envelope developed similar to the failure envelope seen in the monolithic TDA layers tested in previously mentioned shearing. Next slide, please. Looking ahead, next steps in our research will be to conduct shaking responses and system bending response tests at UC San Diego, and then to quantify composite system behavior in different loading patterns. Next slide, please. Some final comments and important reminders are that TDA has a very unique set of strength and deformation properties, making it an incredibly advantageous material. And many applications of TDA are relevant within transportation infrastructure, geotechnical applications, civil engineering applications, etc. And finally, it is important to note that TDA has potential for geotechnical seismic isolation relating to infrastructure, as it has the positives of low settlement, excellent recentering, and very high energy dissipation. Negatives, including that rotations must be controlled, should also be noted, and the use of a TDA LCC composite would essentially create a very good solution in order to prioritize these positives and mitigate any negatives. Next slide, please. And then here are my references, and thank you so much.
All righty. Thank you so much, Camille, for the very informative presentation. A lot of good information there, and seems like some really exciting research you have coming up. I would like to remind the attendees that they can submit their questions via the Q&A widget. Now I'd like to move on to our next speaker, Dr. Somayeh Nassiri, to start her presentation. Again, Somayeh will be presenting on a proposed research project with CalRecycle and the University of California Pavement Research Center on addressing some problems around Caltrans Lean Concrete Base performance. Without further ado, take it away, Somayeh.
Thank you very much, Matt. Can you please confirm if you don't see my screen, just say something. If not, I'm going to just continue.
Screen is
All right,
up.
well,
You're great.
good morning. Thank you for that. Good morning or good afternoon, depending on where you are. And it's a pleasure to be here. Thank you for the introduction. Thank you for the opportunity for us to work on this topic, exciting topic. So, as Matt mentioned, we have not embarked on this project, but we are excited to get started on it. That said, Camille set a very nice introduction into TDA and made my life very much easy. As Matt mentioned, the focus of the project is to look at using TDA in a specific base type material for concrete pavements. And I'm going to get into the details of that. But before jumping into that, a little bit of background about myself. I've been working on various recycled materials uses for concrete applications, various concrete pavement applications over my career. I have worked on recycling glass as a pozzolan for concrete construction and demolition waste, aggregates, powders, other types into concrete, windmill blades, even old planes and scrap parts from plane manufacturing as reinforcing elements for concrete. One of our interesting projects was to transform the chitin component of seafood waste into nanofibers for concrete. I have experience with TDA as a civil engineering application, like a embankment fill, as was brought up in the previous research. But this using TDA directly in a cementitious system is new for us, and we're excited to give this a try. So I'm very excited to get back into recycling research. And with that, some of the motivations for looking at this and for what encourages me as a researcher to get into this is just looking at the sheer volume of the amount of scrap tires, end-of-life tires that are produced on a global scale. It is more than a billion tires. I'm seeing that it is around 1.5 actually billion now. According to more recent reports in the United States, that's in the amount of 280 million tires. And in California alone, it's nearly 60 million passenger tire equivalent. And so looking at these sheer volume and knowing the fact, what we know now about the hazards that come with the stockpiles of end-of-life tires and how they can catch on fire and the amount of disease from mosquitoes, other leachates that they can release into our environment. The motivation and the encouragement to continuing to find a reuse applications for these and taking these out of the stockpiles and putting them into good use is just critical for us as researchers and as implementers, such as CalRecycle. So with that motivation, now I want to give a little bit of background about the application that we have in mind in this project, and then I'm going to tie these two together and show what the hypothesis is, the scientific hypothesis is here. So as a background, for those of you who may not be as familiar with concrete pavement using highways specifically, base layer is the direct layer underneath that top concrete slab, and its role primarily is to provide durable, uniform, stable support for that top concrete layer, concrete slab to sit on. And this is specifically is important during construction, but it's also important during the life cycle, or let's say service life of that concrete pavement, which is very long. It could be anywhere between 60 years or more, beyond that, 80 years, 100 years. We see, birthday parties for 100-year-old concrete pavements. So these are long-lived structures, infrastructure that rely on that base layer to be erosion resistant, to continue to help with the drainage, fast, rapid drainage of any water to be shed to the sides and removed from the pavement, and to also in cold areas to limit the penetration of frost from the top into the subgrade layer, the native soil layer, which we don't want to go through the frost and thaw actions frequently throughout the year. So now one of the types of materials that are used as a base layer commonly is called lean concrete base, LCB. So this is a type of base layer that uses cement in it. to become stiffer and become stronger. But as the name indicates, it is lean compared to structural concrete, the top layer that could have anywhere between 5.5 up to 6.5 sacks of cement. This is only about 3 sacks of cement, which is 300 pounds of cement per every cubic yard. And so the strength requirements are also accordingly lower, which is around 530 psi in 7 days. So then the construction can start. And so it is stronger compared to stabilized layers that just use aggregate base with a little bit of cement to gain a little bit more durability. But it is, very durable, very erosion resistant. It's highly stiff too. So generally, anytime we're achieving a strength by adding cement to the concrete, rule of thumb is that stiffness is also correspondingly going to increase. So we have higher strength, we have higher stiffness. So now the problem with that higher stiffness that concrete pavements occur is that if you look at this diagram, this is schematic. Pavements in general have a very, very significantly larger surface area compared to or relative to their volume. And they're exposed to the elements at the top, they're exposed to drying, and they're exposed to daily temperature changes. And this results in the top layer about 2 inches of the top of the surface of the concrete to dry, whereas the rest of the concrete, especially the bottom portion of the slab, generally remains saturated. So this differential distribution of relative humidity across the slab results in a differential shrinkage, causing the slab to form the shape of a bowl. So upward curvature. We call this either upward curling or warping in concrete pavements. And so with the amount of drying that we get in California, and in fact, in most areas, most concrete pavements after a while become permanently upward shaped. So now the problem with that is that if we use a very stiff base layer such as LCB, it is possible that along the edges, along the joints of a concrete pavement, we could lose support, that very important support that I talked about a minute ago from the base layer. So now the concrete slab is left alone in these regions to work by itself without any support from the base layer. And this causes a very critical situation where when we have loaded axles from the truck falling on critical locations, it can either produce more and more tension at critical locations of the slab and continue to accelerate the amount of cracking that we get in the middle portion. I have a picture of this coming up, or it can result in corner breaks. So overall accelerating the fatiguing and cracking behavior in concrete pavements, but also it could manifest in terms of rougher rides just because of that curling that we have and resulting in a bumpy ride. So this is ultimately this type of cracking is what we're trying to avoid, or at least we're trying to extend the life by reducing or slowing down the type of cracking, this type of pattern that develops in concrete pavement. There is a study, a national study. It is called a long-term pavement performance database, and this includes various test sections that the departments of transportations monitor over the years and provide the data to this national program. And one of the test studies in this program focuses on the base type and compares 3 different base types, one of them being LCB, the other one being an asphalt treated base, and the last one being an aggregate base. And so these studies are indicating that the LCB in generally is showing more transverse and longitudinal cracking over the first 10 years and are generally showing rougher rides compared to their counterparts, which are aggregate bases or asphalt treated bases. Okay, so this was the background as to what is the problem that we're trying to solve. And then on the other hand, we have the tires, the TDA. So what is the plan to bring these 2 areas of focus together? And so this kind of goes back to our years of research on fibers in concrete. I mean, this is a very well-established area of research in concrete that putting fibers in concrete, and this goes back to even ancient construction where they used to put horsehair in concrete or clay bricks or any type of concrete-like material. They used to put straw strands, anything that could form as a tensile tension type reinforcement into concrete to add more to the strain capacity of concrete. So if we don't have any kind of reinforcement in concrete, the load deflection graph shows a very sudden failure type behavior that you can see in this graph where I'm putting my cursor. But if we do add fibers, what you can see is that those fibers past that first crack will bridge across it and still allow the concrete to carry loads. And what you see in this picture is an example synthetic fibers. And so the idea is that if we can emulate what the synthetic fibers are doing in the concrete by cutting the TDA or optimizing their shape in a way that they could potentially have a similar effect on the load deflection behavior of LCB, is it possible that we add to its flexibility? Is it possible that we reduce some of its stiffness? And is it possible that ultimately they can do better in terms of providing a pillow or a cushion underneath the concrete pavement so they don't lose that support along the edges as they do curl and warp over their life? So we did a very, very crude back of the envelope calculation just to estimate, is this even worth it? How many tires would potentially, if this actually works, how many tires will be diverting from landfill or stockpiles? And, a crude calculation shows if we're possibly able to replace 20% mass of aggregate component of LCB by TDA, which I think it's a very high assumption to begin with, using the density of TDA from the literature. We've not measured it yet. And assuming, and this is just a pure assumption, that about 50 lane mile of new pavement is constructed in California. At those rate, we can potentially use 4,200 tons of waste tire every year, which is equivalent to 420,000 passenger tires. So those are just some of our estimates at a high replacement rate. So just looking at the literature a little bit and there are some indicative results that show that we should be able to this kind of benefit from the TDA. This one graph shows results of tension testing on concrete that had rubber particles in them, not necessarily TDA in the form of fibers. And it shows that a higher replacement rate, all the way up to 70, compared to the control, they did have a statistically significantly higher strain capacity. And that is the parameter that we are after. So I strategically looked for some indicators from the literature, and looking at their graph underneath, this is looking at their strain capacity, and with maximum dosage of rubber particles, they were able to achieve about 35% improvement in strain capacity. So there are some indications in the literature that we should be getting that kind of behavior. So now we do know also that we have a challenge ahead of us. And this we know from years of looking at incorporating various type of materials, including synthetic fibers in concrete, is that the rubber in the TDA is a hydrophobic material. And generally, this material is not compatible with a mineral-based, calcium silica-based form of material, which is a cementitious environment, right? So from the literature, if we look at some of the microscopic images of the interface between a cementitious system up top, the lighter gray, and then the rubber, you can see a gap. The gap is clear. And this is not unexpected. Again, these two materials are incompatible, and there are not bonding agents, surface groups desirable to bond chemically with the cementitious system. So what this means is that if we look at the strength results in a concrete material that has rubber in it versus the one that doesn't, so if you look at this graph on the right, the top strength results is for a concrete mix without rubber tire in it. And then look at the very bottom results. That is the amount of reduction that was induced by adding untreated rubber. So the drop is significant between the two. And unfortunately, my y-axis got cut off. I apologize about that. But we do have some tricks up our sleeves for treating materials that are incompatible with concrete. So one of the tricks that we typically our go-to is to fill this gap with powder type material, filler type material that potentially fill the gap, densify the matrix, and reduce the amount of failure that happens from these gaps. And so one of them is silica fume. This is a dust silica. It's a byproduct of silicon metal production. And so when added to the matrix, see the amount of increase, the amount of improvement that was achieved in the strength of that rubber concrete. And that study also provided some evidence, some microscopic images. This is that tire particle that now it's covered with that mineral, with silica fume. And you can see these silica fume particles completely deposited on that tire and helping facilitate that interface not being rubber anymore and more being covered and coated with a mineral type material more compatible with the cement environment and helping with what we call those transitions, interfacial transition zones, which are typically the weak point in any composite material. So another treatment that is typically applied when we deal with these type of materials going into concrete is some sort of a soaking in a solution. Sodium hydroxide is one of them, HCl, mild type acid soaking for a brief period of time, silane, coupling, and just soaking them in liquids that can introduce basically either hydroxyl groups or carboxylate type groups on the surfaces of otherwise materials that are not compatible. And that also shows that this type of bonding can potentially help with enhance the strength. So the reason I introduce these types of treatments is that ultimately our goal is that if we're putting those 3 sacks of cement, which does have a relatively high environmental impact, global warming potential, we don't want to compromise the amount of strength that comes with the material. So if we can, by some kind of mild treatment that in itself is not imposing significant negative environmental impacts, improve that strength, so the construction can still carry on at that time frame that is desired for a rapid, construction lifestyle that we're in this day and age, but at the same time get benefits of flexibility from TDA. That is really the ideal outcome of this project. So we have our standards set quite high, and we're looking to see how challenging this path is going to be, while keeping an eye on literature and some of the results that are available. So just as a brief summary, we are, our motivation are coming from the mission to take away as much as possible and put scrap tires in California in good use, or at least set a practice forward that potentially could create a value-added path for recycling and reusing some of these scrap tires, demonstrating it in California, and hopefully it could set a trend depending on the results that come out. LCB to us is a very good medium for receiving this, because ultimately we don't have high, strict structural strength requirements, and at the same time it is a place that can benefit from that flexibility that the TDA could bring in. And so we find it a good place for trying this out. And as I went over a brief literature review, there are scientific evidence that we could potentially, get some of those higher energy absorption, flexibility, strain capacity from these TDA additions. Some mild treatments may be something that we'll have to try out to treat the interfaces that encourage bonding and maintain a strength in the material, and we'll continue to work on this topic and see if we can come up with a happy medium between recycling TDA as well as still having a durable base layer. So with that, thank you very much for your patience, and here are some resources to our websites in case you're more interested in some of our publications.
All right. Thank you, Dr. Nassiri, for your presentation. A lot of good information there. And, us at CalRecycle, we're very excited about this research topic. And, hopefully it all works out as planned, and really exciting really excited to get started. So
Thank you
now
for the
moving
opportunity.
on. Yes, thank you. Moving on to our last presenters for this session, we have James Gomez and Martin McIlroy from MGE Engineering, and they're going to go over some case studies where TDA was actually used in the field in Yuba County after significant storm damage. So go ahead, take it away, Martin and James.
Okay, thank you. Okay, can everybody see my screen?
Screen's looking good, James. Thank you.
Okay, great. All right, thanks. I'm James Gomez, and I'm presenting today with MGE Engineering out of our Sacramento office, and I'm presenting with Martin McIlroy, also with MGE. Martin and I worked together on this project in 2017, 2018. It was for Yuba County. Yuba County experienced some significant storm damage, as did a lot of the foothill communities in 2017. And so we were tasked with doing roadway improvements for about 14 landslides, road failures, slip outs, and such. So these are images of just a couple of the sites. And so we decided to use TDA, and I think it was mostly at Martin's suggestion that I was unaware of TDA before this project. I've been an engineer licensed in California for 35 years. I've never used TDA up until this project, and it had a lot of benefits for Yuba County. So that's why we decided to use it. I'll get into those benefits here a little more. TDA has been used since the 80s, and it's really a great way of diverting tires from landfill. CalRecycle has a great website for the use of TDA, so I recommend that people take the time to check out the website. I actually used the website quite a bit when I was going through the design process. Here's a map of the storm damage areas in the 2017 Yuba County. It was actually two disasters, but occurred one in January, one in February, and the county decided to lump them together into a design contract. And then we ultimately separated into two separate construction contracts based on geography, so that it made sense to have two contractors, but not under one contract, because these sites are pretty remote and separated geographically. So that's the way we put the PS&E together, and that's the way it was ultimately bid and built. Okay, so it was in Yuba County, 2017, and FEMA declared it a disaster. So we had funding available for permanent repairs. The roads were very rural, mostly 1 and 2 lane roads. No multi-lane roads were involved in the projects that we worked on. Most of the roads were also gravel. Some of them had HMA pavement, but most were gravel. The roads, when they were originally constructed, were not built to any sort of construction or engineering design standards. The roads were started out mostly as timber hauling and logging roads, and the native material was just cast over the side, and so we had really oversteepened slopes and very poor native soils, and so that led to part of these problems in that the fills were never placed into any sort of engineering standard. There was no drainage, and they were starting off with weak soil. So it wasn't surprising that they had as many failures as they did. The project included reconstructed embankments. We had soldier pile walls, and we had MSE walls and gabion walls. So we had a variety of different situations and different wall types in here, depending on what the conditions were. And with that, Martin, can you go ahead and take it away from here?
Great. Thanks, James. So this shows a video of one of the soldier pile wall designs that we did in Yuba County, where we used tire-derived aggregate. It was the type B size TDA that was 6 to 12 inches, or about 150 to 300 millimeters in size. And you can see the truck is end dumping the material at the edge of the excavation, and the excavator is placing that into the excavation behind the wall. One of the great things about using TDA is it is a method specification for compaction, and you do not need to use any water for compacting the TDA material. And this was advantageous for the remote sites that we had. And you can also see the geotextile material on the edge of the wall that was used to wrap the TDA. And I think you can go to the next slide, James. So one of the reasons we looked at this grant and why it was a good fit, we had a lot of different sites, which was going to require a lot of import material. And we needed lightweight material to reduce driving forces on the landslides. And we knew that transportation of the material to the project site was included in the grant. And since this was a remote area, that was also a help in reducing costs. The TDA and technical installation and technical guidance and engineering was also part of the grant. So we had technical specialists from CalRecycle that would help with our designs when we had any questions, and it was a valuable resource for these projects. We also had design levels at about 50% level, so we were able to generate quantities and repair dimensions that were used for the grant. Another thing with TDA is it increased the permeability behind the walls and within the repaired roadways. As a geotechnical engineer, I always say that water takes the path of most destruction. So if we can control the water and drainage characteristics for the site, that helps improve stability. Because we had so many sites, we could use a large quantity of TDA in place of the typical backfill materials. This led to substantial savings to the project costs. And the state grant money also helped with federal matches for funds that were used on these projects. And all told, we had $438,000 grant to provide TDA materials and design these repairs.
Okay, great. Thanks, Martin. And I want to say we could have gotten more money, but that was all the TDA we could use, right? We maxed out the amount of TDA we could use given the site restrictions that we were working with. But had we needed more, we could have gotten more grant money. All right, thanks, Martin. So here's a slide related to the Moran Road soldier pile wall with TDA backfill. So you have a picture here of the fix in its current condition with the soldier pile wall and the repaired slope below. You have a screenshot here of the engineering cross section, and with a couple things I want to point out. The TDA thickness is limited. Oh, geez. That's my, sorry about that. My Apple, sorry about that. It's limited to 10 feet in thickness. You can do multiple layers, but we didn't have that much height to deal with. We used a biaxial geogrid on top to sort of, as belts and suspenders to try to, we realized that we'd have more movement in the TDA as compared to fill. So we wanted to have some biaxial grid to dissipate some of those forces below our pavement section. And we also had to notch out a bit. We used imported borrow because we have guardrail. We wouldn't, in order to be able to install the guardrail post, we didn't want to be going through TDA. We wanted to have support for the guardrail, so we held that back also. So those are some of the things I wanted to point out on this slide. That was the guardrail that I had mentioned. And so in order to get the volume of TDA and to make sure that the contractor knew exactly how to prepare the ground, we did an excavation plan for the TDA sites, which is a little bit in excess of what we normally do. And we normally do finished contour grading and we do wall profiles and such. But because of the TDA, we also did excavation plans, which is what you're seeing here. So this is contour grading for the excavation. Prior to placing the TDA, that enabled us to get really accurate TDA volumes. We wouldn't normally have gone to that extent, but for TDA, we felt like it was important. And also, the engineering is reimbursable under the TDA grant, so any additional engineering you do is eligible for reimbursement. This is just a typical. So with that, this is the layout plan for that site. Looks no different than it would have without the TDA. Just wanted to show that. Here's another example. This one was Fountain House Road. Martin, can you talk about what was going on here?
Yeah, so you can see the damage to the roadway. It completely took out the road. There are two lobes to the storm damage or landslide site that you see here, one in the distance where the cones are, and this one in the foreground. So this is where the road failed, but this was part of a much larger landslide mass that went upslope from the roadway grade. So because of the size of the landslide that was at this location at Fountain House Road, we weren't able to remediate the entire landslide mass because of the size. So because of this rural road up in the mountains, we decided that the risk would be low if we just reconstructed the embankment. So to do this, we wanted to remove any driving forces that would continue the downward movement of the landslide from the roadway grade below. And we also wanted to increase the drainage within the reconstructed embankment so we could increase the stability and also control any ground and surface water that was getting into the site. So TDA offered both the lightweight fill advantage and the excellent drainage. So we tried to maximize the use of TDA within this reconstructed embankment so we could achieve the goals of reducing the driving forces and increasing the drainage for stability.
All right, thanks, Martin. And one thing I want to reiterate here is the native soils were not suitable to be reused as engineered fill. So if we didn't use TDA, we would have had to import. So instead of paying to have imported borrow, we were given TDA delivered to the site near the projects for free. So it was really a win-win for Yuba County, our client. Here's the picture of the repaired condition. This was the same road you just saw in the last slide. Here's a cross-section of what that TDA looks like. Again, we've got the geocomposite layer under the pavement. We notched it for the guardrail posts. We maxed out the 10-foot TDA thickness. We didn't go to a deeper layer of TDA because of the geometry, because of the topography, we had no way of draining it. So we were concerned about placing TDA below an elevation that we could drain via gravity. So we stopped at one TDA 10-foot thick layer for this site. And here's an excavation plan for that site. It looks like kind of like a swimming pool, but we laid out the storm drainage. You'll see here. This was key in determining how much TDA we could use, where our subdrain could discharge to, and so the combination of doing this excavation plan and a drainage plan really led to the amount of TDA that we could use. Here is another site with a soldier pile wall. So in total for the project, we used about 4,100 tons of TDA, and that kept about 410,000 passenger tire equivalents out of the landfill. So So it was a win for the county. It was a win for the environment, using up 41,000 tire equivalents. So performance outcome, the roads and the repairs are performing well since 2018. Martin and I recently visited a few of the sites, and they're holding up really well. Over the years, I have visited the sites from time to time and not noticed any pavement problems or any issues really. The sites are performing really well. So there have been no major maintenance issues to date, other than sometimes some of the soldier pile lagging has been stolen by some of the residents. But aside from theft, the project's holding up real well. Okay, so key lessons learned and takeaways. You have to factor in the grant timing into your project schedule. You know, when you're going to get it out to construction. So you have to work with CalRecycle to get the grant. So make sure you factor that into your schedule. But CalRecycle was very responsive and provided a lot of support. I leaned on them quite a bit through the design process. Followed CalRecycle TDA guidelines for overbuild and to manage post-construction settlement potential. Stage, like, and if you have a situation like ours, we have multiple projects, locations, the grant will only pay to deliver it to the site once. So we selected a TDA fairly central location for each of our east and west construction contracts. And then we had bid item in the contract for the contractor it was furnished TDA, and that was defined in the special provisions as the contractor taking the TDA from the stockpile and delivering it to each individual site. Although the delivering to the stockpile was from CalRecycle. So we had a furnish and we had a place, two different TDA bid items. And make sure that your consultant is familiar with FEMA's integral ground criteria to make sure that you're going to be compensated or reimbursed for the repairs. Yeah, Martin, you want to talk about this one just a little bit?
Sure. So FEMA has a definition for integral ground to support your facility. So for instance, whatever the ground is necessary to support the roadway, whatever that prism is, would be defined as integral ground. And you can use that to justify a longer repair if you're looking at side slopes and excavation slopes. So that is reimbursable by FEMA. So we use that to determine the length and size of the repairs, but also that factored into the TDA quantities that we included for the designs. So it's important to know that criteria, that is FEMA's basis, and then that way you make sure that everything that's included in the repair, those elements will be reimbursable as part of the program.
All right, thanks, Martin. As I mentioned earlier, the 10% of the CalRecycle grant fund is available for engineering technical support. So that helped the county with their engineering costs. And one takeaway that I had, I would recommend using shotcrete facing on your timber lagging for your soldier pile walls, or use precast concrete lagging for added fire resistance. Just a note, if you saw the pictures, that's something I would do now in light of the fires we've had in California recently. And then another key lesson is you have to make it clear that what you're doing is not a betterment, but it's integral to maintaining the integral ground that Martin mentioned, just so you don't get in trouble with FEMA. Don't use language that would trigger FEMA to making costs unallowable, like existing landslide or hummocky terrain or betterment, because you won't be eligible. And then also make sure that you warn the contractor in your special provisions and supplemental information about TDA has potential for puncturing pneumatic tires on construction equipment, because it does have some tire bead, steel sticking out of it from time to time. So track mounted equipment on tracks is the way to go, and as opposed to pneumatic tires if you're going to use TDA replacing it. 10 foot is the maximum TDA thickness. We step the TDA back for our guardrails, and we use the biaxial geogrid below the roadway section to reduce any settlement effects. Gravity drainage, make sure you have gravity drainage at the base of the TDA, and then do a contour grading plan for excavation, just to make sure that your TDA is going to be drained properly. And with that, I'd like to conclude the presentation.
All right. Thanks, James and Martin. Really appreciate good information. This predates my time at CalRecycle, so really, enjoyed hearing about these projects and what a great success they were for the county that went through such severe storm damage. So I appreciate you both for sharing. I think for now we will move on to the question and answer portion of the session. So if you haven't done so already, please enter your questions using the Q&A widget. If you want to ask any specific presenters a question, please include their name at the beginning of your question. So now I'll hand it off to Jake to go through the Q&A from our audience.
Hello, everybody. My name is Jake. I'm from CalRecycle. Looks like we have a few questions today. If we do not have time to get to your question, please do not worry. We will try to reach out and get those questions answered for you. All right, currently our first question is directed at Martin and James. The question is, for rural counties in California seem to experience severe storm damage nearly every winter. Why do you think there hasn't been a significant volume of projects like this since 2017? What obstacles are preventing TDA from being a common solution to these road slip-out repairs?
Well, for me, after I did these 2017 storm damage projects with Martin, I kind of moved on to a very large design build project that basically ruined my life for several years. So I haven't had an opportunity to get back to using TDA. So I don't really know why it hasn't been used more. I mean, what really made it attractive for this project was the remoteness of the sites and the really poor native soils. So wherever you have that situation, I think you makes sense to look at TDA. One thing, and I'm not really aware of the drawbacks, but somebody I think mentioned it earlier about potential leaching of the TDA chemicals from the leaching. We didn't really have that come up as an issue in 2017, but I don't know if there's been any more work done in that area. I'm not sure. I'm trying to think of reasons why people wouldn't have been using it more.
I also think that there might be just there's some lack of knowledge about the use of TDA for these types of applications. I know in 2017 when I talked to CalRecycle, this was one of the first times they were going to use it for soldier pile walls and also MSE. It had been used, I think, in Mendocino County years prior, in maybe 2012 or 2010 for a roadway repair for storm damage. So I think it's awareness, but also I think that engineers typically use tried and true methods, and they're fairly conservative and don't want to use something that they haven't ever used previously. So that could be some of the issue as well, is some of the unknown in the engineering community. And maybe the other reason too is that local agencies haven't hired MGE for their storm damage projects. And if they did, we could use this.
for our presenters, I will go ahead and ask you to stay on camera, and then I'll spotlight you.
Okay, we have a question addressed to Somayeh and as well as Camille. Will adding rubber or tire-derived material to concrete affect concrete's recyclability? Excuse me.
Yeah, thank you for that question. That is a very, very important point, is that when we produce a material, we always have to make sure this material is recyclable at the very end, at its own end of life. And so, this is something that definitely has to be considered as part of the study. It came up also in, at this point, LCB is turned into RCA, recycled concrete aggregate, and used back as an aggregate base again. And this is allowed, this is in the spec, and I cannot see. Yes, this will be introducing new particle, new component. But at this point, I cannot really, pinpoint any obstacles to at least removal, breakdown, screening, because the base layer is lifted, is crushed, and it's screened and sieved out, and then classified again as an AB to be used again as a base layer. So I think, or at least my hope is that we can work with a recycling facility and, expose them to this material. They can put it through their crusher, their screening, and, work with them to see, do you see this as potentially an obstacle, a barrier to recyclability of the material? Camille, feel free to jump in.
I don't have anything to add. I think you covered it very strongly.
Did that answer the question? Is there any specific aspect that you had in mind?
Oh, no, nothing specific. That should be good.
Very good.
And if
Well,
the person asking that question had a follow-up to it, please feel free to use the Q&R, the Q&A web feature.
one of my concerns with using it before we did the project was the performance of the HMA pavement section above, with the deflection from the TDA, with that shorten the life of the pavement. The roads that we worked on were very low volume, and the pavement has performed just fine. So maybe that's a concern why people might be shy about using it, and with higher traffic volumes. I'm not sure.
And, from a pavement engineer standpoint, one thing that, may be overlooked is that the way stress from trucks is distributed throughout the depth of the pavement, by the time you get to embankment, fill material, subgrade level, that stress is dissipated to significantly low levels. And that is ultimately the goal of a good pavement design to begin with. So ultimately, you don't want to be counting on your fill and embankment or subgrade layer to be carrying your truckloads, and that's part of the pavement engineering. So, and I hear you, James, is that, every time you introduce a new material, a new practice, it'll take these demonstration sites, these presentations to overcome some of the unknowns, right? The fear of
Right.
unknown. But the more we do it, and the more it becomes part of the standard practice, and it gets into the spec, the more, accepted it becomes.
Okay. Does anybody have anything else more to say before we move on? Okay, this question is addressed to Martin and James. How did you convince the county to pursue grant funding and TDA strategy?
We said free money.
Yeah.
That was one of the things. But it also, it was a very simple, well, James prepared most of the grant. I was the geotechnical engineer, so I thought it was a very simple grant process. But because we were able to use the grant funding as a match to the federal funds through FEMA, we were able to convince them that this could be a way to go. It did eliminate like tie-back anchors for lateral load on the soldier pile walls. It improved drainage by a lot compared to typical drain rock and other materials. So we were just presenting all these pluses to the county. And we had, what was it, 2 months, I think, or so, maybe a month and a half for the grant application itself. So we still had time even to get everything in. James?
Yeah. I mean, I think it mostly came down to money. They saw how much money they could get through the grant, and the fact that 10% of it could be applied toward engineering. And we could have multiple projects. So with that 350,000, I think I saw, that we could have done that multiple times. So we were actually eligible for a lot more money than we ended up receiving. We just, we didn't need more TDA. So we could have gotten more. But yeah, it came down to money.
Okay. To James, we have a question. Does 1 ton compacted tire bales work?
I'm sorry, I don't. Can you say that question again?
Do 1 ton compacted tire bales work?
Oh boy, I don't know what that is. With 1 ton compacted tire bales, I'm not sure what that is.
Okay, we'll move on. This is for the whole panel. Can you show any one of the case studies or how you manage drainage for any future rainfall events that occurred up gradient of the repaired roadways?
I guess this is for the storm damage repairs. I mean, we use typical drainage designs under drains and the TDA for controlling surface water.
Yeah, I showed on one of my slides that when we treat surface drainage no differently than we would for any other slide, right? So we did have some drainage ditches on the uphill side at the road, and some corrugated metal pipe down drains with dissipators on the downhill side. Like you would, the TDA really wasn't a factor in any of that. So the surface drainage, we treated it like we would any other site. You just don't want to let the surface drainage get into the TDA, right? You have to make sure that you encapsulate it and that you carry the drainage. If you do have to go through the TDA, you need to make a corridor where the surface drainage can't get in there. So yeah, you would treat it just like any other site without TDA as far as the surface drainage.
This question is addressed to the entire group as well. What's one recommendation you would give to a civil engineer or public works department interested in specifying TDA on their next project?
I would encourage them to get on the TDA website and contact the representative to talk about the grant and the benefits. That's what I did a lot of when I was working on preparing the PS&E for these projects.
I mean, we're also available. Our contact information is in the slide, so if you wanted to contact us afterwards, we'd be more than happy to answer any questions. As far as, I don't know, Somayeh, Camille, are there specifications that are developed for the concrete as of yet, or is that still nascent?
Well, as of now, only, mineral aggregate is allowed in LCB. We're far, far from that being introduced into the spec. We're just, kind of starting proof of concept feasibility at this time. But, if we think about the arc of research, it all starts from some feasibility study, then verifying at little larger scales, then verifying, in a stretch of roadway out there. And this could be, a low volume road. It could be like a campus road or some kind of an access road, and then maybe trying it out in a pilot project, and then ultimately, something becoming a standard practice. So it does have an arc of its own, and it'll take time, it'll take research and then verification and demonstration to make sure ultimately what we're doing is safe, for the public, for the environment, cost-wise. We do need to build a supply chain. All of that has to has to happen for something to ultimately show up in the spec.
Okay, that concludes our Q&A session. It's time to bring it back to Matt.
All right, thanks, Jake. And thank you to all of our presenters. Camille, good luck with your PhD studies, and looking forward to our research. Somayeh and James and Martin, it's great to hear from you, and I hope we have some TDA projects coming up in the future with you guys. So I appreciate you all presenting and for making a very educational and informative session. That's going to do it for TDA, and I'm going to pass it back over to Tony.
All right, thanks, everyone. I look at my audio, make sure audio is coming through. Thank you again to our presenters today, Camille, Somayeh, Martin, and James. We finished right on time. We actually have like 6 minutes left. So thank you again for being thorough in your presentations, but also keeping it moving thorough in our questions being asked today. Believe we got to all the questions. If there's any that we did not, there was just a comment in terms of drawings were hard to see. So again, the presentations themselves have been translated into PDFs and are downloadable via in the agenda in the session descriptions. I also want to note that Somayeh had an updated PDF that will be updated probably about 1 o'clock today. So refresh your page and I'll get the newest version of that. Yeah, so I think we're all good for today. So I'm going to just go to our next slide here. So our next workshop in our series is on Thursday, starting at 8:30, and that workshop's going to be part 1 of a 2-part workshop series. And that one is tire-derived products, scaling markets and innovations today and tomorrow. That's going to be a really good session because you're going to have a lot of industry folks on there. There's going to be one presentation that kind of sets the overview, and then excuse me, there's multiple presentations on that day going through there from industry. You can go to the session agenda and click on Thursday, and you'll be able to see. Don't have all the PowerPoints submitted yet, but we're working on getting those and hopefully have them up tomorrow by close of business, and I'll send an email out so you guys can download and see it. We're excited to hope that you will join us for that. And it'll be the same format. On that one, it'll be a continuation that goes to part 2. That's tire-derived products for a market expansion strategies. So on that one, I'm just taking a quick look. That one, the first session will be moderated by Joaquin Wright. And then the next one will be, the follow-up session will be Denise Kennedy. All the people that are on that first session are going to be in the second session, and it's going to be an interactive panel discussion. So we actually won't have a pause and a break on that one. We're gonna leave it open during our break time. So we hope you'll be able to join us on Thursday. So with that being said, I'm going to go ahead and close out. There will be a survey that will be going out to you, if not by the end of day today. First thing tomorrow morning, we need to go through and update our attendance. So your feedback does help us in not only for our future workshop series within this month, but also for the CalRecycle and our tire conference planning team in filling, what we're going to do for our next event. We've gotten feedback that they want to go back to be in person, and so please make those comments like that, because again, it helps advocate what the format is going to be on the future workshop. So with that being said, Kyle, I'm not sure if you wanted to come back in for a second, or if we think we're good to go.
Hi, Tommy.
right.
Thank you. No, thanks for those comments, and we'll see you guys hopefully again on Tuesday.